I'm John Thomas Foxworthy, and today I'm going to challenge a fundamental assumption that I see permeating in our field. The title of this talk is Beyond Bias Removal. I chose this phrase deliberately because I'm going to argue that the common approach to data bias in AI systems, which is essentially detect it and remove it, um, that is basically that is not just incomplete, it's often wrong. So for the next 20 minutes, I'm going to develop a framework for understanding rules with when and how and whether to address bias in your data sets. And hopefully you'll find value within it at the very end. Okay, so how many of you have heard the phrase of we need to remove all bias from our training data sets? This is when what I call an automatic assumption that all biases must be eliminated. It's become almost dogma in certain circles, not everywhere, but it's easy to find. You can find in academic papers, in compliance frameworks, and also in vendor pitches. So here's the uncomfortable question we need to ask. Should we always remove bias? What if these assumptions are fundamentally flawed? What if some of what we're calling bias is actually valuable signal that our models need to have accurate predictions? So I'm going to make a controversial claim. Not all bias is bad bias. Some patterns in data that look like bias actually reflect legitimate real-world phenomenon. And we'll be instead of blindly removing these patterns, what happens is they cause more harm than good. So if you're not going to automatically remove all bias, what are we going to do? So here's a framework. So instead of binary thinking, bias exists, remove it, I propose we ask three critical questions every time we encounter potential bias in our data sets. When should we address this bias? Not all bias requires intervention. Sometimes the bias is our perception and not in the data. Second is, how should we address it? The methodology matters. Poor correction procedures can introduce new problems worse than the original bias. And I'll be getting into this in the slides further along. Third is whether we should address it at all. And this is the hardest question. Sometimes the right answer is to keep the apparent bias because it represents real-world information within our model that we need. This framework forces us to think critically rather than reflexively. It requires domain knowledge, not just statistical tests, and it acknowledges that context matters more than universal rules. To use this framework effectively, we first need to understand what we're actually dealing with. Okay, so here's the critical distinction that most discussions of bias completely miss. There are fundamentally two different types of patterns that we label as bias. On the left, we have unwanted systematic errors. These are the most common that we can identify. These biases should usually be correct, but they're not, such as measurement errors from faulty sensors, sampling bias from poorly designed collection procedures, collection artifacts from inconsistent data entry, and simple mistakes that don't reflect reality. These are problems in our data generation process. They're noise, not signal. But on the right, we have something completely different and difficult to understand, which are legitimate real-world patterns that include true population differences that actually exist, valid correlations that have predictive power, actual trends in the domain, and domain realities that make us uncomfortable but are nonetheless real. So here's the critical point for this audience. Removing legitimate patterns doesn't make your model more fair, it makes it more wrong. The challenge is that both types often look statistically identical. You can't distinguish them with a chi-square test or a t-test alone. You need domain knowledge, you need to understand the data collection process, and most importantly, you need context. So we look further down at the bottom of the slide. Here, we're actually fighting two types of bias in two fronts. First is the statistical bias that's the systematic error that's in your data. Things like selection bias when your sample isn't representative of your population. Second is your cognitive bias in the bottom right, where the systematic error is within human judgment. So, for example, confirmation bias that might cause you to see patterns you expect to find, even though they're not really there. Both of these affect AI systems. And here's the key: your data might have statistical bias, but cognitive bias affects every decision that you make about whether to correct it, how to correct it, and whether to correct it at all. And this is why domain knowledge is critical. Statistics detects patterns, but human judgment determines meaning. And human judgment is fallible. The challenge is that both types of bias often look statistically identical. You can't distinguish them from a chi-square test alone. You need context. So how do we detect these patterns in the first place? So let me walk through the quantitative toolkit for bias detection. These are methods you might want to have in your pipeline, such as distribution analysis, comparing your actual distribution against the expected distribution using statistical tests. And are you seeing what you think you're seeing? If you're sampling from a known population, and does that sample even look right? Second, one of my favorites here is the Benford Laws application. This is particularly common within financial data and also naturally occurring numbers. When human beings, manipulate data, they tend to violate the Benford's law in predictable ways. It predicts the smaller digits like 1 or 2 appear more frequently as leading digits than larger ones, with the theoretical probability of a leading digit D. Deviations from this pattern in real-world datasets can indicate data manipulation or errors. At the very end of the slide deck, I have a implementation, Appendix A, for those who are interested. Next are z-scores and outlier detections. It's a matter of identifying statistical outliers that might indicate either measurement errors or legitimate rare events. The key is knowing which is which. So the presence of an outlier does not necessarily mean that it's wrong. And then there's trend analysis, which is examining temporal or spatial patterns. Is there a systematic drift over time? Are certain collection sites showing different patterns? So to put it in a nutshell here, these methods are necessary, but they're not sufficient. They tell you something is unusual, but they do not tell you whether it's a problem. And that's where the next layer comes in. So statistics gives you numbers, visualization gives you insight. I cannot overstate the value of EDA, exploratory data analysis, which is simple tools of histograms, box plots, scatter plots, heat maps, etc., that often reveal patterns that are sophisticated, sophisticated tests often miss. Now, the human eye is exceptionally good at pattern recognition. Use that as well. Look at your data. I mean, really look at it in a deep way. But here's where the domain expertise becomes absolutely critical. You can stare at a distribution all day, but if you don't know what the distribution should look like in that domain, you can't interpret what you're seeing. And that is why I've become skeptical of purely automated bias detection systems. Numbers alone never tell the whole story. You need subject matter experts. You need people who understand the data collection context. You need people who can recognize domain-specific patterns. The most dangerous phrase in data science is that the algorithm found a pattern. The question is that pattern real or is it an artifact? So once we've detected something that might be a bias, how do we decide what to do about it? So the next is the decision framework. So here are 4 questions, key questions that I recommend to ask about bias correction. First question is it a measurement error or a collection artifact? If yes, the correction is usually appropriate. These are mistakes that are in your data generation process. The second question is about sampling bias and does it reflect real population patterns? This is harder. If your sample is skewed because of how you've collected the data, then that's sampling bias. But if your sample actually reflects a skewed population, that's reality. For example, positively skewed populations are income distributions, real estate prices, taxation levels. And then negatively skewed populations are human lifespans, grade point averages, daily stock market returns, things of that sort. And then the third question is, will correction actually improve model performance on real world data? This is a validation question. Don't assume correction helps. You need to test it and use holdout data that represents your deployment environment. And then the fourth question is, do we have sufficient domain knowledge to validate this correction? If you don't understand the domain enough and whether or not the pattern is legitimate or not, you need to be very careful with removing it. So ultimately, the key insight here is context-aware decision-making beats universal rules. Every domain is different. Every data set has its own history. There is no one-size-fits-all approach. So let's see what happens when you actually forget about this. So here are 3 ways bias correction can go wrong. I've seen this in production systems in the past 20 years doing data science, machine learning, and artificial intelligence. And in the 20 years, overcorrection is pretty common. This is when you remove so much variation that you destroy a valuable signal. Your model becomes less accurate because you've thrown away predictive power along with the bias. The statistical properties may look great, but the model performs worse in deployment. So I've seen teams spend several months debiasing a data set to achieve some type of perfect demographic parity in their metrics. And then they watch their model fail in production because they removed features that actually have predictive power. The second one is quite insidious. It's when your correction procedure itself introduces systematic errors. Common culprits of this is when you have improper imputation that changes the data set. So if you have a missing value, let's say you place an arithmetic average when you should really put the number next to it, or maybe a median. Another culprit is reweighting of schemes that amplify noise, and also synthetic data generation that doesn't capture real correlations. So you end up fixing one bias only to introduce more 3 or 4 biases altogether. The third one is the validation challenges. How do you know your correction actually improved things? Your fairness metrics, have your fairness metrics improve, but did your real world outcomes improve? Your test set looks better, but can it generalize? So there's a series of questions within validations. So the problem here is that we often validate corrections using the same mindset that generated them, rather than using real world deployment data. So within AI systems, there are some special considerations. So AI systems, usually modern deep learning systems, have some unique bias characteristics that we need to understand. The first is bias amplification. This is a surprise for anyone who's in production, sometimes when you first see it, such as a machine learning model that can take small biases in the training data set and then amplify them during learning. A 5% imbalance in your training data can become 20% with your model's predictions. This happens through an iterative learning process where the model learns to weight certain features more heavily, which creates feedback loops in particular. And then the second one is really feedback loops in deployed systems. This is particularly dangerous. Your deployed model creates data that goes back into training future versions. If your model is biased, it generates biased data, which trains more biased models, which get bias amplifications across versions. And here's the uncomfortable truth that we need to discuss, basically between the trade-off between fairness and accuracy. So maximizing fairness metrics often reduces predictive accuracy. Not always, but often. And you need to explicitly decide which matters more for your specific use case. There's no getting around this trade-off. If you're building a recommendation system, for example, maybe you want to optimize for fairness. So if you're building a medical, for example, diagnosis system, you probably want to also optimize for accuracy, but you have to make that choice explicitly and document it. Theory is nice, but let's look at what happens in practice, so to speak. So here's some 2 use cases in the real world that I've worked on. First one is an international import-export company that learned this lesson pretty much the hard way. The company was building a machine learning model to predict shipping delays for their global supply chain. During their bias audit, they noticed that their model heavily weighted countries and port features in a particular way. These certain countries had certain ports that consistently showed higher delay predictions. This looked like a geographic bias in terms of where they are on the map and potentially discriminatory treatment of certain regions. Their ethics teams raised concerns. The company didn't want to seem as discriminating against developing nations or specific regions, so they made what seemed to be a responsible decision. They removed country and port identifiers from the feature data set. In other words, making it country blind and also port blind. And here's what went wrong. These geographic features weren't reflecting bias. They were reflecting real operational realities. Port infrastructure generally differs from region. Some ports have state-of-the-art automated container handling. Others are severely congested with outdated equipment. So when they remove these geographic features, their models delay, its prediction actually dropped 28%. That's a massive fall in logistics. That went from being able to accurately predict which shipments needed to be expediting to essentially guessing. The company lost millions of dollars in expediting, and also the company lost millions of dollars in expediting costs. It missed delivery windows. It had customer penalties because they couldn't accurately predict where delays would occur. So the lesson here is that geographic data captured operational realities, not discrimination. So let me show you what happens in the opposite situation. So this is a matter of keeping the bias. Here's a case where I worked on where the apparent bias turned out to be a legitimate signal. A team building a credit risk model noticed that the zip code was strongly correlated with default rates. This looked like a geographic discrimination, in other words, redlining by another name. The team came very close to removing zip code entirely from their feature set, but let's look at why keeping it was correct. Zip code was acting as a proxy for legitimate economic factors such as local employment volatility, cost of living relative to income, regional economic conditions. These are real risk factors that affect someone's ability to repay a loan, which is the definition of credit risk. So this correlation wasn't reflecting bias, it was reflecting economic reality. In other words, if your neighbor is going bankrupt, so are you. So certain geographic areas generally had higher economic volatility, and that affects default rates. When they tested removal on the validation data, defaults increased by 22%. That model couldn't accurately assess risk appropriately without this geographic information. So the key insight here is that not all correlations with protected or sensitive attributes are discriminatory. Sometimes they're picking up a legitimate signal that occurs in the real world. So in terms of a practical assessment, let me give you some practical tools that you can work on that's helpful here. On the left here is a bias assessment checklist. I recommend integrating into your data quality pipeline, which is document your entire data collection process, identify potential bias sources before you look at the data, conduct statistical tests, but don't just stop there, create a comprehensive visualization suite, consult domain experts. This is not optional. It is something that you must do. Validate everything on your holdout data from your deployment environment. And then there's key questions to ask, which are, how is the data collected? How is the sampling? What's the sampling methodology? What is the sampling method? Is it random, stratified, etc.? And furthermore, so in the interest of time, let me go a little further here. So context matters. Here's a fundamental insight that no universal solutions can be applied for data bias. Every claim that I've made today is a qualifier. It depends on your domain, it depends on your data collection, it depends on your deployment context. So here's a three-step action framework. Step one is to understand your domain deeply. Step two is to know your data collection process intimately. And step three is to consider your deployment context carefully. For knowing your domain deeply, what patterns should you expect? What are your known risk factors or correlation structures? What does your scientific literature say? You cannot you cannot be a good data scientist without having some type of domain knowledge. And then for your data collection process, and to know it intimately, a critical factor here is what errors that might exist, what is your sampling methodology, and whether there are any changes in the collection procedures over time. So if there's any regime switching in the data, that will affect your data bias. And then step three, will your model face similar data in production? Are there any distribution shifts that you need to account for? So let me leave you with some three key takeaways. First, not all bias should be removed. Learn to distinguish unwanted systematic errors from legitimate real-world patterns. This distinction is the foundation of everything else. Second, context and domain knowledge are essential. Statistics alone cannot tell you whether to correct bias. You need to understand what your data represents and where did it come from. Third is decision frameworks that beat prescriptive rules. Resist the temptation to create universal policies. Instead, build frameworks that force contextual thinking. And here's a major point here is to take away is that be suspicious of anyone that are offering simple answers to bias questions. Data bias is complex. It requires nuanced thinking. Anyone claiming to just do X probably hasn't put a lot of thought into it. And here at the very end is my last appendix of the Benford's Law application. And that's it.
Thank you so much. This was a really interesting perspective. So first, this division of bias into errors to fix versus legitimate real-world patterns, this is from Kiri Wagstaff, I should say,
Okay.
reminds us to ask that the purpose of the learned model or to ask what the purpose of the learned model is. Is the goal to learn from the past and reproduce it, or is the goal to learn from the past informed by desired behavior to achieve better outcomes? Do you have a perspective on this?
That would be the former. We want to learn from the past. We want to see what the data is telling us within the feature set that is able to regress, as in the definition of regression means. In other words, if we go back in a particular period of time and we're trying to predict the next data point or to forecast a negative point, we want to see if those features actually do a good job of explaining and also predicting that type of behavior. And that'd be my way of answering that question. I think there's another question that Kiri had, or is that it?
No, there was just a compliment.
Okay. Okay.
I actually had a question on this. So you mentioned the importance of integrating expertise. How do you see sort of procedurally setting up the best way in which to integrate expertise in what you're identifying as a pretty complex problem?
Buy them drinks? No. No, I'm only joking. So, each organization is different. There's one way is to find somebody who has the IO experience within an organization, which is the industrial organizational psychology that exists. There's always somebody that people point out, that's the SME, even though they don't even know what SME means and you want context. But at the same time, my recommendation, which I would strongly go, is not to do the introduction blindly. Do a lot of your work, understand your data thoroughly, do exploratory data analysis. If there's been any changes within the data sets that have changed, or if the infrastructure has changed, know that very well before you bring into the subject matter experts. I think too many people tend to go to them immediately, trying to ask them for help, when really we need to do a lot more homework, because that way they'll really appreciate your perspective and you'll be able to get more out of the conversation and the relationship.
Thank you so much.